Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 22nd lecture on the SwayamPrabha course titled Maritime Structures, offered by Department of Maritime Engineering at IIT Gandhinagar. This lecture is a sequel of the last lecture 21, where we started discussing the fundamentals of lateral torsional buckling that can happen on beams. In this lecture, we will take up a design example and show how to check or assess the existing beam design for lateral torsional buckling failure using Eurocode and Indian Standard Code of Practice. Lecture 22 on LTV design example. Welcome to the class. We already said lateral torsional buckling can happen in for different reasons. The primary reason being deep web and long span beam, and therefore it can have a lateral movement, lateral displacement, as well as a long deflection, and the web, which is a compression member, starts buckling because of its deep web parameters. This happens when the member is having a very less strength against lateral torsional buckling. So, what are the factors which will contribute to lateral torsional buckling? One is the material property. So, essentially if you look at material property, then I must say the system or the material should have large modulus of elasticity and a high shear modulus. So, if you choose a material, especially let us say steel is one of the most preferred construction material for maritime structures. So, steel cross section or the steel grade, if you remember the lectures on material designations and properties, we already said the steel is also graded based upon the Young's modulus and yield values. So, we should have a composition alloy of steel whose modulus of elasticity is fairly high and it also possesses good shear modulus. Looking at the cross sectional dimensions and span of the beam, we can say the cross section should possess high torsional constant and warping constant, and the moment of inertia about the weaker axis should be also relatively higher. Okay? If we have these conditions met, then LTB can be avoided. Look at the boundary condition, that is the support conditions of the beam. If the beam is enabled bending about major axis or minor axis and the beam is enabled with warping, then for sure the beam is a candidate for lateral torsional buckling. Let us talk about the load. We already know that every point load of high magnitude is always a reason or a cause for high deflections, which we already know as an engineer. Similarly, in lateral torsional buckling, if you have got loads with the high amplitude, then it may result in LTB. It can be a point load, it can be even uniform distributed load spanned across the entire length of the beam. So, what are the various buckling modes with lateral restraints that can avoid LTB? First, let us look at the most favorable cross sections which can avoid lateral torsional buckling. One is a solid circular member, the second can be an I section loaded this way. Please understand, the web is loaded, not the flanges. If you keep the member like this and load it here, web becomes a compression member. Okay? In this case, the load is vice versa. So, it is loaded this way and this is the length of the beam, okay, like a H beam, not an I beam. And if it is a box section, which is very commonly preferred in industrial structures and maritime structures topside, because this space can be useful for carrying pipelines and conduits for any emergency purposes, which should not get damaged in case of fire or any other dropped objects. Generally, this kind of casing can be fire resistant and one can carry the electrical HVAC or internet cables through these kind of hollow sections, so that they can be protected from fire. So, if you have a box section of HW of this category, then these three sections are preferred, which can be a very strong candidate against lateral torsional buckling. For example, if you do not provide any restraints to the beam, so the beam is free to buckle due to lateral torsional buckling, and that is how this end up. So, there is a lateral motion, there is of course a vertical motion, and of course at this point there is a twist. So, twisting, lateral and buckling will result in LTB. If the compression flange alone is restrained, then lateral torsional buckling is not possible. Okay? If the compression flange, for example, if this is the beam spanned over L meters, this is the deflected profile of the beam. So, this becomes a compression flange and this becomes a tension flange. If the compression flange is restrained for its entire length, generally what people do, they embed the compression flange, okay, they embed them in concrete. This is a compression flange, they embed them in concrete. So, they hold the compression flange against lateral buckling for the entire length of the beam. Okay. So, if it is done, then LTB can be avoided. If the flange in the tension side is restrained, as you see here, then this will result in distortional buckling. That is quite dangerous, friends. If you restrain the tension flange, then it is not advisable. If you do not put any restraints at all, then LTB will anyway occur, and if it is slender flexible web, then buckling is more severe. So, the web properties, the boundary conditions make an important contribution or a candidate vulnerable to lateral torsional buckling. The most preferred cross sections are as you see on the screen. Now, let us take a design procedure to explain LTB. The step number 1 in LTB assessment is to compute the critical elastic moment MCR. Okay? It is a primary design parameter for checking beams against LTB. MCR is defined as the maximum value of the bending moment supported by the beam free from any imperfections. The elastic critical moment of a standard section which is double symmetric. Okay? For example, I section, one axis of symmetry, another axis of symmetry. Okay? A box section, one axis of symmetry, another axis of symmetry, and so on. So, if you have a double symmetric section, the elastic critical moment MCR, which is one of the primary design requirement equation, is given by this. Okay? Let me call this equation as equation number 1. One can also use the modified 3-factor formula for single symmetric sections. If I got a single symmetric section alone, let us say if I have a T section, okay, this becomes an axis of symmetry. Let me draw this T section again. Okay. So, now this section has only one axis of symmetry. So, if I have single axis of symmetry, then I find out MCR using something called 3-factor formula available in the literature. Friends, maritime engineering course or maritime structures being a candidate for multidisciplinary engineering entry levels, the detailed discussions and derivations related to hardcore structural engineering and structural mechanics is not the focus of this course. So, though we substitute them with relevant equations available in the international codes of practice. However, for knowing more about the basics of derivations of these equations, I request you to go through the detailed references given in the course web page, so that your knowledge can be further reinforced to these equations. For the time being, friends, let us believe that we know how to arrive at this equation, because the fundamental of arriving this equation has been discussed in the previous lecture. Please have a look at that. So, if I know how to compute the elastic critical moment for a double symmetric section or a single symmetric section, which depends on 3-factor formula C1, C2 and C3. Okay? 3-factor formula. So, what are these values? Of course, they are available in the code, but we will discuss that. So, if I know the equation for MCR, then I can always check what is the MCR actual and what is the MCR on demand. So, let us compare them and assess the safety of that candidate against lateral torsional buckling. We will take an example now, and we will solve this example using Eurocode. A figure shown here is subjected to 2-tier loading. One is about 10 kN per meter and other is about 6 kN per meter, 2-tier loading, simply supported beam. So, the figure shows 5.7 meter long simply supported steel beam. Okay, the section is 356 by 171 by 51. You may be wondering how this 1 mm coming. Actually, it is because of the unit conversion from FPS to MKS to SI unit. So, therefore, there is a small confusion here, but however, the steel grade of the cross section is given here. So, 356. So, H is 355. Let us look at the properties of these. Okay. We are bothered about the height of the section, we are bothered about the depth of the section from the roots of these flanges, okay, thickness of the web, thickness of the flange, and so on. So, height of the section is 355. The breadth of the section is 171. So, the height is 356, height is 356, breadth is 171, okay, and thickness TW, TF, thickness of the flange is 11.5 millimeter, thickness of the web is 7.4 millimeter, and this radius is about 10.2 millimeter. These are properties as per UK steel section standards, and this beam actually is UK beam 356 by 171 by 5.1. Okay, this property is anyway available in the code of practice, so one can easily borrow these data directly from the code. Now, the member is subject to tire loading, as you see here. Consider that the beam is laterally unrestrained. For the entire length of the beam, the compression flange is not restrained. Okay? That is the most vulnerable case, as we saw in the previous slide. So, check the stability of the beam against lateral torsional buckling. That is the question asked. We will use Eurocode for this. Okay, friends, we will take a simply supported beam, span is given, cross sectional dimensions are known to me, and therefore, now I am going to assess this for LTB. So, let us first find out the maximum bending moment coming in the cross section. So, to find the maximum bending moment, I must know the partial load factor for dead load and imposed load. So, we will use Eurocode EN 1990. As per EN 1990, the partial safety factor gamma F for dead load is 1.35, for imposed load or live load is 1.5. So, let us compute the factored loads as 1.35 times of 9.58, okay, which is the dead load, okay, the dead load, and 1.5 times of the live load. This is the live load. Okay. So, I get so much. So, MED is about 91 kilonewton meter, which is the demand. The beam has sustained this. Okay, that is the demand. Let us try to also classify the section. We know in maritime engineering, section identification is very important. Okay, classify them. Yield strength is 275. That is given in the problem. Okay, it is steel 275. This number indicates yield strength. The yield strength is 275 megapascal. Okay. The maximum thickness in this cross section, if you look at 7.4, 11.5. The maximum thickness is 11.5. Let us pick up that number and check, is it less than 40 or more than 40. Okay. If it is less than 40, Eurocode 1993-11-2005 on table 3.1 refers this classification. So, refers as per 5.2 table, then epsilon is calculated, which is 235 by Fi, which is 0.92. Okay. So, if the flange is under uniform compression, let us try to see what is the outstanding flange. So, if you look at the figure here, this is my radius closure, this becomes my outstanding flange, which is set as C, which is computed by this equation. B is known, that is breadth of the flange, then TW is known, thickness of the web, and radius of this is also known. Okay, this radius is also known, right? This radius is also known. So, using this equation, I can find some factor called C, and if I try to find out C by TF, and if it is coming to be less than 9E, then I will classify this as class 1 element. Okay. Please refer to Eurocode table 5.2. So, now I classified steel as class 1 element. Further, let us try to find out the internal compression part, the web is in bending. Okay. So, that is given by this equation where h is the depth of the web, 2 Tf is known, 2 R is known, I get this. Then I will compute what is called C by Tw, then I would compare this value with 72E. Then if it is so, then I will classify this according to class 1 element as per Eurocode 1993-11 table 5.2. Then I compute something called moment of resistance of the section. This is demand. Okay. And now I am going to compute the capacity. Okay. So, the capacity or the resisting capacity of the section is given by this equation as per Eurocode part 3. Okay. So, one can easily substitute these values and try to get the section modulus plus section modulus, which is WPT. For a specific section, the plastic section modulus can be either computed or it can be available from the steel tables. So, substitute this value and Fy is known to me, gamma MO is taken as 1.0, so I get this value. Now, since MBRD is greater than the demand MED, the section is safe against bending. As I said, bending is parallelly happening with lateral torsional buckling. So, one need to check whether the section is first of all sustaining flexural bending or not. If the beam is not sustaining flexural bending itself, then there is no assessing possibility to assess it for LTB, because lateral torsional buckling is a second stage of assessment. The first stage is to check whether the beam is safe against bending and shear. So, we have checked it safe against bending. Okay. Now, I want to check the beam for safety against lateral torsional buckling. Okay. Calculate something called elastic critical moment MCR. Let us use that equation what we already know and let us take this and try to find out. So, in this equation, MCR can be obtained for the following factors. The beam is simply supported, therefore, the effective length factor which is used as Kw in this equation is taken as K zeta, okay, is taken as 1 if it is simply supported. Now, I am going to apply the load only at the top flange, therefore, Zg will be half of the section depth. Okay. Zg, what we see here, is only half of the section depth, because I am going to apply load only in the top flange. Okay. So, Zg is actually h by 2. So, we know this value. From table 3.4, I try to get the factors C1 and C2, C1 and C2. I try to get this factor C1 and C2 from table 3.4. Now, we also know from the table the moments of inertia, the torsional constant, the warping constant, shear modulus of the section and E. These are all given in the table. For UKB 356 by 171 by 51. So, I have to have chosen a steel section, because section is safe in bending. I chose a section, then I compute MCR, because I can use this equation to compute MCR. Okay. I compute MCR. Then I compute something called buckling factor, okay, for lateral torsional buckling. So, which is similar to the slenderness factor. So, which is given by this equation, and this value is found to be 1.423. For a hot rolled steel section, we can say referring table 3.1 of Eurocode 1990 for h by b, h is the depth and b is the breadth, which is more than 2, we can use buckling curve C. Okay. So, from table 3.8 for curve C, alpha LT, okay, is taken as 0.49. Now, I compute phi LT. Phi LT is given by this equation where I need alpha LT. So, I have taken alpha LT from table 3.8 for the curve C, buckling curve C. How do you check buckling curve C? This value will decide what buckling curve should I use. So, now this value decides to use it to C. So, I look at C, table 3.8, and I have this equation with me where I am substituting them and getting ILT as 0.42. Okay. That is a limiting value. So, we got this. So, for simply supporting a uniform distributed load, we will have this factor Kc as 0.94. We have it in table 3.9 of Eurocode 1990. Please have a look at the table. So, I will get Kc. Once I know Kc, I will substitute all the values. Kc is now known, and of course, LT is already known. It is already known. Okay. Then I compute this. If less than 1, which is under uniform distributed load, then I compare this MBD with MGD and check against LTB. Take gamma M1 as unity. So, MBD is given by this equation where psi LT is now known to me, F is also known, Fy is known, gamma M is known. This I will assume from or take it from the table 3.9. So, I try to find out this ratio, which is 0.87. So, it is something called unity check. Okay. 0.87 less than 1, the beam is safe and stable against lateral torsional buckling. No additional restraints are required. Let us take one more example which we are going to use with IS 800, Indian Standard Codes of Practice. Now, we have a data to design or check the beam. The beam is simply supported over a span of 8 meters. We are using a different problem now. We have chosen a section ISMB 400. You know what is ISMB 400? This depth is 400 overall. Let me draw it clearly. If we have an I section, the overall depth is 400. The CG is here at center, and for 1 meter of this section, it weighs about 62 kg. Okay, 62 kg. The total moment under the UDL acting on this beam is given as 50 kilonewton meter. Take steel 50 grade as Fe 250, check the beam for LTB. So, I know the area of this section, I know depth of the section, I know thickness of the flange and web and thickness of the width of the web. All these are given in steel tables. So, open up steel tables, check for ISMB 400, you get all these properties. Okay, please have a look at that. Having said this, the moment of inertia Iy by Ixx are also known to me. So, you see Ixx is very high compared to Iyy, therefore, Xx, which is the horizontal axis, okay, is taken or called as major axis. The vertical axis is called as minor axis. So, I know these moments of inertia. They are available in the table, you do not calculate them. Okay. Now, I classify the section based on these properties. Fy is known to me. I can calculate epsilon, I can calculate B, then I can fulfill these conditions, then I will classify the section as plastic section. which is given in IS 800-2007, table 2. So, we will classify the section now. We say the classification is plastic. Then I compute this ratio H by BF less than, it should be less than 1.2, as 2.86. So, for ideal conditions, it should be less than 1.2. Is it less than 1.2? No. Let us see what is TF value, thickness of the flange. It is 16 millimeters, which is less than 40 millimeter. So, as per table 10, the buckling class is about x axis is A and about y axis B. So, IS 800 helps me to classify the buckling class also based on the cross section. Now, having said this classification, let us now compute MCR. Okay, MCR is given by an equation similar to what we discussed in the morning lecture or earlier lecture. Class 8.2.2.1, you have this equation. So, I know the E value, I know Poisson's effect, I know shear modulus, I know moment of inertia about the weaker axis, okay, very important, weaker axis. I substitute them here, and for LLT of 1.0, L is 8 meters. I look at table 15, class 8.3, for a fully torsional restraint but warping, not restrained both the flanges condition. So, then I compute something called torsional constant. Okay. For open sections, it is given by a simple equation like this: sum of BTQ by 12, I compute that and compute I tau. So, if I know I tau, can always again further compute the warping constant from this equation for an I section, where beta f in this equation is given by this relationship, where IFC and IFT are given by this relationship, BDQ by 12 relationship, and HY is given by this equation. So, I substitute them back here and get IW as warping constant as so much. Once I know IW, once I know BF, then I can always compute MCR. MCR is coming to be 95. So, the critical demand of the beam is about 96 kilonewton meter. Then let us check the design. MD as per class 8.2.2 is given by this number. If it is a plastic section, take beta B as 1, and ZP is the plastic section modulus, and FBD is a design bending compressive stress. So, let us take this FBD given by this equation, where psi LT is a bending stress reduction factor, which is now included in IS 800, which is accounting for the LTB effect. So, this can be computed from this equation, where phi LT is given by this equation. Alpha LT is an imperfection parameter taken generally as 0.21. Therefore, the non-dimensional slenderness ratio lambda LT is now given by this equation, and we have also check whether this condition is satisfied. There is a symbol here, okay, whether this condition is satisfied. So, we do that, then we get the plastic resistance capacity for this section ISMB 400 as so much, the elastic capacity is so much, and lambda LT is again verified, which is 1.75. Then we can say it is okay because this condition need to be satisfied. Then I get phi LT computed. So, lambda LT is now known, alpha LT is now known. I substitute them, I get phi LT as this. Once I get phi LT, I compute xi LT and found out this to be 0.284. Okay. Now, I want to find the design bending stress. The design bending stress is given by this factor multiplied by Fy by gamma m naught, where gamma m naught is a partial safety factor to resist buckling. Generally, it is taken as 1.1 as recommended by IS 800. So, once I know these values, I find FBD. Now, the bending strength is governed by the lateral torsional buckling. Therefore, the bending strength is governed by these factors multiplied with FBD. I take this plastic factor, I take ZP, I take FBD from here and compute this. Now, the applied moment is 50 kilonewton meter, friends. You see here, the applied moment for which the beam is to be designed is 50 kilonewton meter. We must be having it here in the beginning definition of the problem. Let us check. So, we have computed the design bending moment. Okay. So, 50 kilonewton meter without any safety factor for loads enhancing. So, I get this value as 50 kilonewton meter. Okay. So, ZP and ZE are known for a section, then I use 1.1 for partial safety factor and then I compute this MD as so much. The applied moment is about 50, the capacity is 76. Okay, the beam is safe against LTB and no restraints are required. So, friends, lateral torsional buckling abbreviated as LTB is a serious concern in long span, slender beams. So, what we should do is, as per the recommendation given by IS 800, we must select sections carefully. So, one of the important recommendation is select something called compact sections. Usually they will be safe against LTV. Okay. So, in this lecture and the previous one summed together, we discussed how the vertical load for a long span beam gets this shifted and the cross section is twisted. So, it has lateral and longitudinal along the length of the beam is bending, lateral along the breadth of the beam is bending, lateral bending, and of course, this rotation initiates torsion. So, lateral torsional buckling under vertical load happens on these conditions of beams which needs to be assessed. We have discussed two examples where one is solving using Eurocode, other is solving using Indian standard codes of practice. Friends, I hope you understood both the sequel lectures and LTB. So, you would have realized that how we can assess an existing beam for safety against LTB without going into much derivation of how to get this MCR equation from the fundamental principle mechanics. However, for reinforcing your knowledge and better understanding, please look into the references of the books cited in the home page of this particular course and learn more about the mechanics which helps you to derive this equation of the MCR value. Otherwise, one can use this directly from the Indian codes of practice and say how I can assess an existing beam in this. Friends, for industrial structures and maritime topside units, LTB is one of a serious concern, and therefore, one should know if use double symmetric or single symmetric steel sections, the sections must be checked in principle for lateral torsional buckling. However, if the section is chosen carefully, okay, fulfilling all requirements of warping constant sufficiency like we see here. If we can choose the section carefully, then one can avoid the lateral torsional buckling. One of the important tips is make the compression flange laterally supported, choose solid sections of this order, choose sections with high warping constants and torsional constants. If you do that, then these sections are called as compact sections, designated as plastic or compact sections in course of practice. So, these sections by default will help you to resist or stand against lateral torsional buckling. Remember friends, LTB is not because of axial compression happening on beams, it is a vertical load happening on beams, because the long span and deep webs, they initiate failure through a buckling mode, which is also coupled with torsional effect. We call this as lateral torsional buckling. Thank you very much friends. We will discuss further in the next lecture. Namaste.